Hello, welcome to Physics World. This is Mrs. Homberg, and we're continuing our study of current electricity by focusing on Kirchhoff's circuit law. What can traffic patterns and toll booths tell us about circuits? We can imagine that toll booths basically jam you up. They make things harder to go through when you're on a trip. Well, imagine that having only one toll booth is like having one resistor. Everyone kind of has to get through that one toll booth. What if you had 3 toll booths in a row? Now, all of the cars have to go all through all 3 resistors, all 3 toll booths. However, when they open up parallel toll booths, it makes it a little bit easier. People split up, they come in all together as a big, large group, they divide, split up against all the toll booths, and then pass through. Kirchhoff did not just study voltages, he also studied currents. He made the analogy that one big river would split into streams, and therefore you could be able to determine, if you knew all the current going into a node, a junction, a point, then you could see that it would split up into other remaining wires and be considered a stream. So you're basically going from a lot of water in a river to smaller streams when you come to a fork in the river. Likewise, let's say you had 2 small streams coming into a junction, a node, a point. Then, of course, all that water adds up and makes for one big river. Kirchhoff's junction law, it tells us what happens to current as it goes through nodes and different branches of a circuit. You can see on the left-hand diagram that what flows in flows out. In other words, all of what goes in must equal the sum of everything that goes out. Notice that on the right, it's been turned into a circuit schematic with straight lines for wires and the labels I1, I2, I3 for current. So how could you write a current equation for the node shown in the center? What would it be? Well, if we notice, we have several currents going in. Which ones are those? You have I4 pointing in, you have I2 pointing in. What goes in must come out. Which currents are pointing outward? I3, I1. So you could write what goes in, sum of the currents in equals sum of the currents out. Let's see, what goes in? I2 and I4. I2 plus I4 must equal what goes out? I1 plus I3. We can write similar equations for these circuits. I'll do the first one, then you should try the next 2. What goes in? I1 plus I4 equals what goes out? I2 plus I3 plus I5. Go ahead and complete the other 2, and then we'll compare answers. Let's compare answers, and that middle circuit is really important. Notice that the current that comes in here comes up against a node where it splits up into 3 sections. But what happens as I2 approaches this node, I3 approaches this node, and I4 approaches this node? They're going to merge again, adding themselves all up to make I5 come out. So what goes in at this node is I1, and what comes out is I2, I3, and I4. That makes for the first half of our equation. But what about the second half? We can see that I2, I3, and I4 are coming in, and I5 is coming out. This is going to happen over and over in the circuits that we solve. So I suggest we keep this in mind as what goes in comes out, and what goes in comes out again on the other side. Our last one is pretty basic, similar to our first one. All right, we are now getting closer and closer to what we do with our circuits. We're going to analyze our current. We call the current that comes out of the battery either I total or I battery. This current comes out, and if you notice, if we follow along the wire, it's going to go through R1. In this case, then, we understand that IT is the same as I1. So if you wanted to analyze using the Kirchhoff circuit law with current here, then we would say, all right, at point A, what's coming in? I total, I battery. What's coming out is I1. So that would be, at node A, what our equation would be. IT equals I1. Notice that I1 continues through R1 and flows into node B. This is the only wire that has current going into node B, but then it splits up into I2 and I3. This is really important for our circuits because we might know I1 right away because it's the same as I total, but then we're going to have to work with splitting up this big river into two small streams. If I1 goes in and I2 and I3 come out, at node B, we'll have this equation. What can we say about node C and node D? See how that's basically one big wire? That is really an identical situation. And what happens is, what goes in comes out. Well, if this is the current that came out of the battery, we know that because it's a closed loop here, it's the same as the current that's going to come in. So I total out equals I total in. So when you, on the other side of these resistors, see that I2 feeds into this node, I3 feeds into this node, I2 plus I3 are going to add up to I battery again. You're going to see that you can use these tricks to find out what current is going through what parts of the resistor.